we're going to be talking about ADD, but before we do that, this is blood flow. Hyperperfusion in the brain, where the brain is getting lots of oxygen and glucose, or hypoperfusion, it's not getting a lot of oxygen and glucose. This is the average or mean level of perfusion. This is 2 and 3 standard deviations of increased perfusion, 2 and 3 standard deviations of decrease, and the solid lines are statistical significance. Delta, this is EG frequency across the x-axis, goes from DC, or 0 cycles a second, on up to 40 cycles a second. The delta band is actually positive perfusion. During your slow wave sleep, your brain is busy doing things. You're not awake, but your brain is still busy. So we actually have delta as a positive perfusion. All of this is work out of UCLA's NPI lab. Ian Cook and Andy Luchter did the studies. This is basic neurophysiology. The theta and alpha band up to about 10, 11 ends up being hypoperfusion. The 11 to about 16 is a neutral positive perfusion. And at about 16 hertz on up, it goes into hyperperfusion. You have to think of the brain being at rest with the alpha and theta state, idling, gently on for the SMR band, and quite actively on for the beta and gamma band. In ADD, there was a study by Ernst Niedermeyer. Niedermeyer is really famous. He should be. And when he writes a paper, you read it because he's, a foundational figure in EEG. And he wrote a paper talking about the frontal lobe disconnection in ADD. The frustrating part about that was he didn't talk about what was the disconnection. Where is this disconnection? And what we basically find is that he didn't tell anybody what circuit it was. He just said the frontal lobe and the motor strip are disconnected. Well, that was frustrating enough for me. Frustration leads to investigation to try and solve it. Now, if you look at this, there isn't much frontal lobe here. This is a Mac monkey brain, and these stippled areas that are somewhat colored up are called suppressor strips. If you stimulate the suppressor strip, you inhibit an associated area. And area 4S is the premotor, supplementary, supramotor area in front of the motor strip. And area 4 is the motor strip. There's obviously a relationship there. Is it cortical? Is this just a direct connection across the surface? Or how does the frontal lobe connect? And there's already been studies in ADD that have shown the head of the caudate being disturbed, the frontal lobe not being as dense with gray matter. There's various locations that have been identified as being off in ADD. Interestingly, this is area 4S and area 4, and the circuit goes from the surface down to the head of the caudate, over to the putamen, globus pallidus, to the thalamus, and then up to the motor strip. This circuit is the ability of the frontal lobe to inhibit motor activity, thus the ability to stop hyperactivity. If you add up all of the neurochemistry here, there's a net excess of 1 GABA. GABA is an inhibitory neurotransmitter. Some more activity in this 4S gets less activity at area 4. This frontal lobe can inhibit the motor activity. If the cingulate becomes involved in this circuitry, it goes frontal lobe to the caudate, to putamen, globus pallidus, subthalamus, thalamus, and then up to the motor strip. That little twist, that little sidetrack that was thrown ends up adding another GABA. It becomes a double negative. So the frontal lobe stop command becomes the command stop stopping. Thus the perseveration, the obsessive compulsive stuck on that can happen with a cingulate. This inhibitory circuit can become a perseverative circuit if the cingulate becomes involved in it. This circuit can be an on or an off, depending upon whether the cingulate's involved in it or not. Now, in ADD, ADHD, there was a group of over 400 kids in Australia. This is work by Bob Chabot, Robert Chabot at NYU, and Gordon Serfontaine in Australia, who's long since passed. These patterns were separate clusters of patterns that look similar. And this is delta, theta, alpha, and beta. And you can see in this first one, there's an excess of the theta and kind of deficit of the beta, a theta-beta ratio issue. Others had an excess of theta, but it had quite a bit of beta. This wouldn't be a theta-beta issue. There's actually there's beta there. This person has theta, but also alpha. What they found is about half of the kids had a theta pattern as their failure mode for their ADD. About a third of them had alpha as their failure mode. About 15%, just shy of 15%, were normal at rest, and about 10% basically had a beta spindle as their pattern. Now, much more recently, basically starting with this paper, the identification of the beta spindle subset of those that had ADD was something people had to address. It wasn't always just too much theta and not enough beta. This one doesn't have enough theta and it's got an excess of beta. They realized there were all of these. These are obviously subtypes of or subsets of the ADD, ADHD population. But ultimately, the theta pattern and the alpha pattern and the beta pattern are different endophenotypes. And they're genetically linked patterns that end up being involved in this. Here's the caudate, head of the caudate, the frontal lobe to the caudate to this aspect of the circuitry ends up being a piece of that network that we looked at here. That's this piece. So what else is comorbid with ADD, ADHD? Tourette's. People that have ADD, ADHD, the hyperactive kids quite often have a comorbid Tourette's tic. The head of the caudate creates a motor tic when there's a discharge in the head of the caudate. The tail of the caudate merges with the stria terminalis and impinges on the amygdala hippocampus. If the tail of the caudate has a discharge, the amygdala will give you emotional content and the hippocampus will give you memory content. So emotional speech, Tourette people sometimes blurt out intensely some words. In the left hemisphere, it would be words. In the right hemisphere, it would simply be sounds, like a animal grunting or groaning or moaning, or just sounds, not words. The hippocampus gives you echolalia or parroting. When you hear something, you repeat it. It's like an echo back. If somebody says something, they repeat it back. Now, obviously, that's as annoying as can be. And if you've ever had a sister or a brother who did the parroting back thing, you're ready to pound the hell out of them after a few minutes of them parroting back stuff. So it's socially annoying, but the Tourette person doesn't have a choice. These are involuntary discharges. And in Tourette's, we see about a third of the people with Tourette's actually end up having visible EEG discharges. And for those Tourette patients only, an anticonvulsant can end up helping with their Tourette's. We had a kid, a psychiatrist in the Bay Area, sent their EEG data through. We interpreted it and said, oh, look, an epileptiform discharge in the temporal area, and he's got Tourette's. We're not trying to get him diagnosed as epileptic, but we suggest an empirical trial and an anticonvulsant. We'll see whether the tics go away with an anticonvulsant. Sure enough, a low dose of anticonvulsant, Lamictal, basically lamotrigine is the generic, the brand name Lamictal, and the tics went away. The parents got totally freaked out because it was an anticonvulsant, and so they went to UC San Francisco Med Center, to the neurology department. They did their own EEG, and the neurologist basically said, well, you're on a very low dose. Well, we weren't trying to stop seizures. We were just trying to stabilize the brain. In a psychiatry, they don't treat epilepsy, but they saw the lamotrigine as something unneeded because there was no discharges in their EEG. And they basically suggested that they stop taking it. Now, it wasn't their prescription to alter, so they actually screwed up. You have liability if you change somebody else's prescription. You need to talk to the doctor who prescribed it. You don't tell the patient to quit it. But they said, quit it. So they pulled the Lamictal. The kid started to tick again. Now the parents are totally freaked out. They want to meet with me to explain all of it. I said, I'll be happy to meet with you, but you have to get the neurologist in San Francisco and their EEG and your psychiatrist and me and our EEG all together at the same time so we can actually explain all of this. It took a little while to get the logistics of this worked out, but we got the neurologist and me and the psychiatrist and the parents and the EEG from the doctor and the EEG from us. We looked at the neurologist's EEG, no epileptiform discharge. There's a phrase that the neurologists use: the absence of evidence isn't evidence of absence. Just because you don't see something doesn't mean it's not happening. You just don't see it. I parroted that back to the neurologist. You didn't see anything in your EEG. Doesn't mean there isn't something happening. It means you didn't see it. We then looked at the EEG we had recorded, and he had to agree, yep, that's a spike. Then suggested that altering somebody else's prescription isn't exactly kosher. The neurologist is a little squeamish about having to admit it, but yeah, you're right. I should have contacted the psychiatrist instead of altering the prescription. The empirical evidence is that the Lamictal stopped the tics. The spike was there. The Lamictal stopped the tics. The spike wasn't there anymore. You pulled the meds and the spikes came back. You tell me, should they be on this medication or not? And the neurologist had to agree. It was the right call, and they made a mistake. The motor tic and the guttural utterances can end up being something that may be triggered. Again, about a third of them that we see, we can see a spike in the EEG, and only for those people do you give them an anticonvulsant. If you give an anticonvulsant to everybody that has Tourette's, most of them won't respond because it's not a preponderance. It's like 30%. If 70% don't respond, it's not going to look like a successful drug trial. But if you use a biomarker to guide the medication selection, at that point, it works beautifully. We've got the brainstem coming up, a projection to the front of the head, but there's also an ascending sensory fiber that has collaterals into the brainstem. This is the lemniscal pattern. This is the extralemniscal. And this is a sensory relay, somatosensory relay of something coming up to the somatosensory cortex, but it stimulates the brainstem. The multisynaptic ascending reticular activating system is stimulated, and that ends up stimulating the entire brain. If you see an alpha rhythm in the posterior areas of the brain in the sensory area, it's a sensory relay that's idled. But if you see alpha up in the front, what's making it? Well, it's the diffuse thalamic projection system. It projects alpha everywhere from the thalamus, and it does spare the primary sensory areas. So occipital poles, the primary auditory cortex, and to a certain extent, the somatosensory cortex will end up being spared this innervation. But the frontal lobes get it. Now, why does this system exist? Well, if you hear the snap of a twig, you shouldn't just activate your auditory cortex. You might have to get up and get moving to save your butt from something that broke that twig. So the general activation of the brain from asensory input is a very adaptive thing. Now, even the image of a twig snap may end up triggering you if you've heard a twig snap and then got mauled by a bear. So, PTSD probably has some aberrant stuff going on with all this arousal stuff with simply the image of something that used to be a caveman's problem. I should warn you that these are human dissection. This is to show basically caudate, putamen, globus pallidus, thalamus. They don't zigzag around quite like that line drawing. They're actually adjacent to one another in a subcortical location. People do beta training. Here's the base period. Here they're training beta up. Here's a rest period. Now they're training beta up. Here's a rest period. Beta train, rest, beta, rest, beta, rest. You can see beta went up during the training of beta, and it went down during rest periods. There are people that will say they trained beta and it did not go up, and they're right. There are also people that say that they trained beta and it went up, and they're right too. How can they both be correct? It's the kind of measurement you're using. If you're looking for how big beta is, beta doesn't get bigger, but there's more packets of beta per unit time. This is magnitude, the average, the integral average of amplitude. If you're just looking at the amplitude, the size of the beta, beta is always going to be small. If you're talking about midgets, midgets don't get big, they stay midgets. But if you fill a room with midgets, you've got more midgets. So this is like how many midgets are in the room and fewer. And so when you're training beta and you want to see the increases, you have to average it across time and see the change in magnitude. QEEG does magnitude. Raw waveforms, you look at amplitude. So if you're looking at the raw waveform, the beta didn't get any bigger, but there are more beta packets per unit time. If you add them up, you can see these increases. So the people who said they trained beta and it didn't go up are correct. It doesn't get any bigger. I mean, it's always going to be small inherently. 1 over F, the faster the frequency, the smaller you're going to be. This explains the argument between two people that are both right and adamant that the other person is wrong. They're right, but so is the other person. This is actually a paper that was done by Yuri Kropotov, talking about induced beta that you basically get because of a task. And this is a normal person. This is a high functioning ADD measured by a CPT task, a continuous performance task like an IVA or a TOVA, test of variable attention, or basically it's a task that's going to tell you you have to hit the button or you shouldn't hit the button. This is a go signal. And this is a joint time frequency analysis, JTFA, from 0 to 74 cycles a second, and from time 0 to 1,100 milliseconds later. So this is a second worth of data with a brief base period just before it starts. They were given a signal that tells them they had to hit the button. So about 500 milliseconds later, the brain responds to that signal by turning on beta at the F3 location, because you have to hit the button with your right index finger. Their button push happened at about 700 milliseconds. So there's a 500 milliseconds for conscious awareness, and another couple hundred milliseconds for your reaction time. And this is normal. But you also have bursts of gamma, 1, 2, 3, 4, 5, number 6. 6 bursts of gamma in a second. The gamma is nested in theta, and that's for motor function. So bursts of gamma in theta nests. Now here's a high functioning ADD. They did pretty well. I mean, they're beta synchronized. It didn't happen at 500 milliseconds. It was slower, and they had a reaction time that they pushed the button here at 756 milliseconds. So 3/4 of a second later, they actually hit the button. 1, 2, 3, 4, 5, 6 packets of gamma, but they're awfully weak. Now here, these are robust bursts of gamma, chirps of gamma. Gamma chirps in theta nests. What are we, a bunch of bird brains? So I don't make up these terms. Some bird brain made up those terms, but you can see the gamma bursts or gamma chirps in the nests. They're all there. Here's a low functioning ADD, and their beta kind of sort of almost synchronizes. It's a little late. They hit the button at 904 milliseconds just before the time runs out for the next trial. So and you can see that some of the chirps are missing from the nests. So there's a gamma deficit in this patient as well. There's a bit of a weak gamma in even the high functioning ADD compared to the normal person. And this is, again, brief bursts of theta, brief bursts of gamma. Persistent gamma is pathology. Chirps of gamma is normal. You can see pathological gamma in thalamocortical dysrhythmias with pain, movement disorders like Parkinsonism, tinnitus, focus and epilepsy, some forms of reward deficiency, some eating disorders, obsessive compulsive, depression, those kinds of things. So there's gamma that can be pathological as well. There are people that try to tell you that gamma is great stuff, you should train more of it. You need to realize gamma's situationally good, but situationally could also be a bad thing. You don't necessarily just train it up randomly in anybody. You end up having to find people that have low amounts of it and train it up. In the 1970s, there was a Dr. Scheer, I think Scheer in Houston. And he created the school system in Houston. You have to remember the early 70s, we didn't have the DSM like we have it now. And kids were labeled as brain damaged, minimal brain dysfunction, retarded, learning disabled. I mean, they had all sorts of classifications, but they weren't really well done classifications. They were just something wrong inside, some kids not learning right. And the school system basically gave them to him to evaluate. If they had no gamma at all, he assumed that they were in fact probably brain damaged and couldn't make gamma. If they had some but not enough, like the low functioning ADD or the high functioning ADD, but without enough gamma, he would take them into his program and teach them gamma. At the end of 1 year in his program, they were put back into the school system, going from brain damage, retarded classifications, and again, very gross classifications. These aren't even politically correct terms to use anymore. I have to wash my mouth out with soap for having said them even. They were put back into the school system. They were classified as superior to bright kids at that point. So, they weren't really brain damaged and retarded. They were just in need of some specified training to get their brains working better. And the gamma training in those learning disabled kids ended up giving them the ability to perform at a high level.
We'd like to welcome our new gold supporter, NeuroGuide by Applied Neuroscience. Advanced features that make NeuroGuide the best for professional mental health care providers and researchers. Conventional and quantitative EEG at the same time, imports from 45 different EEG amplifier formats, EEG auto artifact rejection without phase distortion. Download the free demo now at appliedneuroscience.com/NeuroGuide.
You can see the deficits in this slide. The beta spindle variety of ADD, you can see the beta spindle here. These are frontal electrodes. These are frontal electrodes, and these are frontal electrodes. And this is 1 second. And if you counted all the little wiggles in the 1 second, this is beta up into the 20-something hertz range, as is this, as is this. The front of this person's head is full of excess beta. Beta spindles. These beta spindles are, by definition, abnormal if they're bigger than 20 microvolts. Well, 50 microvolts, basically a millimeter here. And these are more than a millimeter. These are excessively sized and clinically abnormal by very definition. If you read Ernst Niedermeyer's book, Clinical Electroencephalography, and that's a preposterous title. If you call your book Clinical Electroencephalography, you got to think, well, who the hell thinks they can write that? Well, Niedermeyer and Lopes de Silva together wrote that book, and they earned the ability to use that title. A fabulous compendium. And what's it, 7 editions now that it's gone through? I think 7, maybe 8 now. I don't know. But it's like the unabridged dictionary or encyclopedia set about EEG all in one text. And he says beta spindles larger than 20 microvolts are by definition abnormal. And this is an abnormal amount.